For example, if you take the limit as x approaches 4 of x squared minus 2x minus 8 all over x minus 4, you'd first check what is going on as x approaches 4. So as x approaches 4, the numerator is approaching 16 minus 8 minus 8, which is 0. And the bottom is approaching 4 minus 4, which is also 0. It's the indeterminate quotient 0 is 0, the exact case that L'Hopital's rule applies to. So it states now that we can go ahead and take the derivative of the top and the bottom separately and reevaluate the limit after the fact, and it'll be the same as the original limit. Now, in former sections, we would have just factored and canceled, most likely, right? So certainly a possibility here. We could try to take the factored form of the numerator and see where it coincides with the bottom. So here's a common factor of x minus 4. Cancel that. And now as x approaches 4, this will approach 6. And so we get 6 over 1, which is 6. Okay, so we have a method for dealing with these. L'Hopital's rule is a little more efficient in many ways. Okay, so using L'Hopital's rule instead, right, see how that works. So x approaches 4 of x squared minus 2x minus 8. I don't need to factor anything. Sometimes it could be very difficult to factor depending on the type of problem you have. These are quadratic, so it seems very simple just to do this. But if they were larger polynomials, polynomials of larger degree, our factoring skills would wane very quickly, and we would not know what to do in those circumstances. So this is extremely useful in a broader context. So as x approaches 4, we have a 0, 0 case, so I'm able to take the derivatives according to L'Hopital's rule and reapply x approaching 4. So the derivative of the top is 2x minus 2. The derivative of the bottom is 1. So we have the right-hand side complete. I should go ahead and try to reapply x approaching 4, and it turns out we will get 2 times 4 minus 2. We no longer get zeros. And so we have 6 just as before. Okay. Another example. Let's take the limit as x approaches infinity of the natural log of x quantity squared over x. Okay? Now, even though I didn't state it before, it is true that L'Hopital's rule applies even when x should approach plus or minus infinity. It won't matter. Okay? So the fact that it's not a finite value a is irrelevant. L'Hopital's rule still applies. Okay? So as x approaches infinity, the natural log of x also approaches infinity. Right? And the square of that is certainly approaching infinity. And the bottom is x itself, so that's also approaching infinity. So we have another indeterminate quotient. So L'Hopital's rule applies. And let's see what it should read. So this limit, as x approaches infinity, the natural log of x squared over x should be the same through L'Hopital's rule as the same limit of the quotient of the derivatives. So the derivative ln x quantity squared is a chain rule, so the 2 comes down. The natural log stays the same inside. The inner function stays the same. And the 2 goes to a 1. I don't need to write any parentheses with that. This is fine how it is. But then to complete the chain rule, I'll multiply by the derivative of the inner function ln x, which is 1 on x. Right? Again, this is outside the natural log function now. Right? Just completing the chain rule on the numerator. Again, separately from the denominator. The derivative of the denominator is just 1. All right, so let's clean up a little bit and see what we have. We have the limit. I don't need an h here because I'm not doing L'Hopital's rule again. I'm just cleaning up what I have. So we'll get 2 ln x on x. Okay, so L'Hopital's rule is not sufficient apparently at this point. As x approaches infinity, the bottom approaches infinity, and so does the top. The natural log is still very slow going, of course. Natural log is the slowest growing function you're aware of, but it's still heading towards infinity. So, since it's still an infinity over infinity case, after L'Hopital's rule was applied once, we can apply it again. So let's see what it yields this time. So we'll now have the limit as x approaches infinity of the derivative of 2 ln x is 2, 1 on x. The derivative of the bottom derivative of x is just 1. So now we just have limit as x approaches infinity of 2 on x. Or you could take the 2 to the outside, doesn't matter. And write 1 on x in here. Either way, the only thing that's approaching infinity now is the bottom. So as soon as you removed the infinity over infinity, the coupling of the two infinities, as soon as you remove that scenario, for sure you'll have a knowledge of what the limit is at that point. In this case, it's clearly 0. As the bottom grows without bound and the top stays fixed, you're heading towards the value of 0.